Alright, in this video you're going to learn about the relationships between all the various graphs of motion. First you have a position time graph, you have the velocity time graph, you have the acceleration time graph, and you have the jerk time graph. And as you know, and we've talked about already, is that velocity on a position time graph is really just the slope of a line segment or the slope of a tangent line when you have a curved line segment. That is also true for acceleration on a velocity time graph and jerk on an acceleration time graph. So in order to find velocity on a position time graph, you're going to find slope. In order to find acceleration on a velocity time graph, you take the slope. In order to find jerk on an acceleration time graph, you're going to find slope. Now that takes care of just the one jump. So from position to velocity, velocity to acceleration, and acceleration to jerk. Now what happens if you start seeing curved lines on graphs? Well, in the case of a position time graph, a curved line shows you some kind of acceleration. And if it's an upturned curve, it shows that you're speeding up or becoming more positive. So if you've got a negative acceleration, you're moving towards zero. And if you have a positive velocity, you're going to get more towards infinity. And we can describe this as a smile. So if you're looking at a slope or a curve that looks like a smile, then you're talking about some kind of positive acceleration. Now this also is true for going from velocity to jerk. So in other words, if you see a curved line on a velocity time graph, you're also looking at some kind of change in acceleration. So in other words, you're changing speed at a faster accelerating rate in the positive direction. Now similarly, if you're slowing down or speeding up in the negative direction, you're going to see a downward shaped curve, which you could view as a frown. Now you also have that same thing happening in from a velocity time graph to a jerk time graph. So you're accelerating at an increasingly negative rate. So let's sort of take a look at that on a graph. Alright, so if you look at this position time graph, you'll see two curved segments, one between 5 and about 20, and another between 20 and 30. So if we were to try to find velocity at various locations around the curve from 5 to 20, you're going to take tangent lines. And you're going to go around the curve and tangent lines at each location. And that will show, and if you look, you've got a high negative velocity on the far left hand side and a relatively high positive velocity on the other side, and a zero velocity when the curve is at the bottom. Now again, that's forming that same smile we saw in the other on the chart before, and you can see that you've got that upward shaped curve. Now if you look at between 20 and 25 here, in those two segments, you've got a downward shaped curve. Therefore you're looking at alright, so reviewing, to find velocity on a position time graph, you take slope, and that's also true for acceleration on a velocity time graph, and jerk on an acceleration time graph. And if you want to figure out what's happening as far as acceleration goes on a position time graph, an upward shaped curve is going to show speeding up, and a downward shaped curve is going to be showing slowing down. And that's also true going from a velocity to jerk. Now what happens when you want to figure out displacement from a velocity time graph, or velocity from an acceleration time graph, or even acceleration from a jerk time graph? Well, in that case, really looking at slopes. So here we have a velocity time graph where we're looking at and we want to find displacement. So you want to take each of these shapes and break them into segments. All right, so we have that triangle that runs from 0 to 6 minutes. And if you want to take the area of that, remember the area of a triangle is 1/2 base times height. So you plug your numbers in and you get an area of 18 meters for that. Then you have your rectangle right there, which gives you another 18 meters. The orange triangle from 9 to about 12, and you can find the acceleration is 9 meters. You have a -9. All right, you've got -18, and again -18. So we have all of these individual segments that we can collect. Now, if we wanted to find the total displacement, so now we can find the displacement, distance, we could find slopes, we could find average velocities, as well as average speeds. So let's take a look at that quick. All right, those are our various areas. And if you add up all the areas, including the signs, you get a displacement of 0 meters. And if you add up the absolute values of all the areas, you get the distance and 90 meters. All right, average velocity, of course, is displacement divided by time. So your average velocity is 0 meters per minute. And average speed, being distance divided by time, is equal to 90 over 25, or 3.6 meters per minute. Now, of course, if I wanted to find the acceleration at a given point in time, you're going to go back and you're going to find the slope, which we've done a number of times, and that happens to be it's a flat area, so it's -6 minus 6 over 15 minus 9. So you get an acceleration of -2 meters per minute squared. So what this means is if you want to go from a velocity time graph to a position time graph, you're going to take the area between the 0 and the x-axis. Same thing holds true from acceleration to velocity, and again from jerk to acceleration. So if you look on the simple things, you can figure out how to move from one graph to another, both from down the chain, which would be derivatives, or up the chain, which would be called integrals in calculus. And that is a summary of how to find information on various motion graphs.